For today, let's look at exponential growth and decay. Here are the formulas associated with those. So exponential growth, the keywords you're going to find in the word problems is going to be increases over time. And your formula is y equals a times 1 plus r to the t power. If you see something like the word decreasing over time, well, that's exponential k. You notice the difference. It's the same formula except for
subtraction.
You're subtracting r. Now, a is going to be our initial amount, so what we start with. R is our rate of growth or decay, and notice this should be as a decimal here. So if you have something like 90%, then that should be 0.9. And t is our time, the length of time you are increasing or decreasing. We're also going to talk about half-life, and here's the formula for half-life. Y equals a to the 0.5, because my rate is half in each time, to the power of t over lambda. And I'll explain what this means when we get to it. But this lambda is basically representing your half-life. How much time it takes for your material to reach half its existence. Half-life, half-time.
I'm freaking zoned out for a second.
Right there.
Oh, I always do that.
Now, first problem. In 1995, a magazine had 14,000 subscribers. The number of subscribers increased by 40% each year thereafter. Write and use an exponential growth function to find the number of subscribers in 2016. So my keyword here to tell me it's a growth is increased. So I'm going to use the formula y equals a to the 1 plus r to the t power. Where a, my initial value, is what number? 14,000. How many subscribers I start with?
I used to subscribe to a magazine in 1995.
You signed up
Oh yeah.
through mail or something, or phone call. My rate is going to be 40% as a decimal. What is that? 0.4. And then my t for time, well, I'm starting at 1995. I want to see how many subscribers I have all the way to 2016. How much time has elapsed? 21. Yep. 21 years. So t is 21. Now you just want to plug this into your calculator. 16,398,978 subscribers.
Or you can buy some copies online.
Pretty big number. But as you see here, that's a pretty ridiculous increase. You're doing pretty well for yourself if you're growing 40% each year. In reality, this is probably like 1 or 2% at best. But hey, 14,000 to 16 million in 21 years, they're doing pretty well for themselves. This is an example of an exponential growth. Now let's look at a decay. Kate drank an energy beverage with 150 milligrams of caffeine. Each hour, the amount of caffeine in her system decreases by 12%. Write and use an exponential decay function to find the amount of caffeine in her system after 8 hours. So the key thing here to tell me about a decay is the word decreases. So I'm going to use that y equals a to the 1 minus r t. So let's look at a. My initial value is what? How much did I start with in my system? Yep, 150. And it is decaying at a rate of what?
0.12.
Very good. 12%, so 0.12. And how much time am I calculated for? 8 hours.
Ocho.
Right there. So now, I just plug that in my calculator. And I get roughly about 54 milligrams of caffeine.
Yeah, you know what they say about cousins?
Like so.
Okay.
So you start off with 150 milligrams, you're decaying by 12% each hour. After 8 hours, you'll just have 54 milligrams. Now, let me have you try this one. A garbage dumpster started with 4 pounds of garbage. The amount of garbage increased. I'm going to erase this because we're not going to talk about continuous yet. It increased by 35% each day from this point forward. Find the amount of garbage in the dumpster after 2 weeks. Okay, what's my keyword here to tell me if this is a growth or decay? I am increasing.
Yes, sir.
So y equals a to the 1 plus rt. What is my a value? Should have put 4 pounds. What is your rate of increasing?
0.35.
Yep, 0.35.
We think your blood.
And what is my t for time?
14.
Aha, so notice this is increasing each day, and after 2 weeks, that gives you 14 days. So pay very close attention to the vocabulary. And that gives me 267, let's just round pounds of garbage.
Lightweight.
Now, one more type of problem. If you're in physics class, you have seen this already, I'm pretty sure. The half-life of mercury 197 is 3 days.
Oh my god, this is radiation.
So we know that, let's just say somebody told me I'm going to die at 80 years old. That doesn't mean my half-life is 40, right? Because when I die, I'm still going to be decaying. But I'm going to decay pretty quickly, right?
Yeah.
But then I'm going to decay slower and slower and slower and slower.
Okay.
This is where you get kind of like, fertilized bones, right?
Oh, okay.
Where it's like just basically rocks.
Yeah.
Oops.
Okay.
So half-life is the half time that an element is gone. It's still, you're about halfway there. Now write and use an exponential decay function to find the amount of mercury 197 left from a 50-gram sample after 20 days.
Ah, shit.
So let's see here. Half-life was y equals a to the 0.5, that's my rate of decaying, t over, let me get this right, lambda, sometimes you'll see h here. But basically this represents what is that material's half-life.
Tree.
Okay, so what is my a value? What's my initial sample I'm starting off
50
with?
grams.
50 grams. It is decaying at a rate of half. How long? What's my t?
20.
My t is 20 days, yep. And I have to divide that by its half-life,
3.
which is 3. Usually you're just going to see it written as so. Just a sentence, the half-life of such is whatever. So 20 over 3. Plug that into your calculator and you get,
5.5.
yes, 0.49 grams. So after 20 days, that's how much of my mercury 197 is left. You would think, let's see, if it's half-life, you would think that would be 25 grams left after 3 days, which is correct. But you're thinking, wow, it's losing 25 after 3, then it should be gone in 6 days, right?
Yeah.
If it's halfway there, 3 days, it should be gone in 6. Well, that, again, decay, it happens fast, but then it slowly steadies out. So that's why we still have something after 20 days. It's just a little small something.